Welcome to Spring LIB.
In this problem, we are told that we electrolyze molten Kf with a current of 10 amps for 2 hours. So this is Kf, and in aqueous solution, that means that we have K plus and F minus ions. And we want to determine the volume of F2 gas that we produce. So that means that F2 gas is a product. So to go from F minus aqueous to F2 gas, we know that this is the half reaction that corresponds to, meaning that F minus is oxidized to F2 gas. And that must mean that K plus is reduced to solid potassium. And that corresponds to this half reaction where we add an electron to aqueous K plus to plate it out as a solid metal. And so since F2 is a gas and we want to find the volume that it occupies, and we are given a temperature and a pressure, then we must need to find the number of moles of F2 that were produced so that we can use the ideal gas law in order to find the volume. So for F2 gas, we electrolyzed for 2 hours. And if we convert that into seconds, then that's 3,600 seconds for every hour. And we applied a current of 10 amps, so 10 coulombs per second. And according to Faraday's constant, there's 96,485 coulombs for every 1 mole of electrons. And based on the oxidation, for every 1 mole of F2, we have 2 moles of electrons. So that's 2 moles of electrons and 1 mole of F2 gas. So now we are left with units of total moles of F2 gas. When we multiply out those ratios, that comes out to about 0.373 moles of F2 gas. And now we can use the ideal gas law to solve for the volume. We know that the ideal gas law is PV equals nRT. So to rearrange that to solve for volume, we know that that is nRT over P. N is the number of moles, which we just solved for. That was 0.373 moles of F2 gas. R is the ideal gas constant, so 0.0821 liters times atmospheres per mole times Kelvin. The temperature, when converted to Kelvin, is 298. And the pressure is 1 atmosphere. So the volume of F2 gas that was produced after running this current was about 9.12 liters of F2 gas. Now we also want to determine the mass of potassium, and potassium was reduced, so the solid potassium was plated out. So we set up the same ratio, which is 2 hours for the length of time that we ran this current. Converted into seconds is 3,600 seconds per hour. And again, the current was 10 amps, so 10 coulombs per second. Faraday's constant is 96,485 coulombs per mole of electrons. And now, based on the reduction reaction, we see that for every 1 mole of solid potassium plated out, we have 1 mole of electrons. So this time the ratio is 1:1. So 1 mole of electrons corresponds to 1 mole of solid potassium. And now to find the total mass of potassium that was plated out, we use a molar mass to say that 1 mole of potassium corresponds to 39.10 grams of potassium from the periodic table. And when we multiply that all out, we should get a final answer of about 29.2 grams of solid potassium that was produced. And we also want to determine in which compartment of the cell each one of these reactions take place. Well, we see that F- was oxidized into F2 gas, and K+ was reduced into solid potassium. We know that oxidation occurs in the anode and reduction occurs in the cathode. So therefore, this 9.12 liters of F2 corresponds to the anode, since that's where oxidation occurred. And for the solid potassium that is produced at the cathode, since that is where reduction took place.